Thank you very much. Now it's recording. Thanks a lot. So I have forgotten. Yeah, thank you, Kevin, as well. I did not notice that. Merci. So during previous lectures, I mean, we deal with photon number state of n, which essentially the photon number state of n, they were complete bases, and we use them for expressing a specific wave function for photon. And then we say that we are interested to understand what is uncertainty principle for quadrature. And we define the quadratures that we are dealing with x1, which was a plus a dagger. Guys, please correct me if I do any mistakes, because I don't remember usually the notation that I use. And then we had a minus a dagger divided by 2i. And these two, x1 and x2, they were our quadrature. And for photon number state of n, we did the mathematics and we calculate what is delta x1 power of 2. And we did also the calculation, found what is delta x2 power of 2. And we found that that is given by 1 divided by 4, 2n plus 1. And that one was 1 divided by 4, 2n plus 1. Okay. So they were the uncertainty that we had for the quadrature of x1 and x2. And we say that explicitly, we are interested in the case of vacuum because delta x1 times delta x2, that is given by 1 divided by 4 for vacuum. Okay. And essentially, for any photon number states, delta x1, delta x2, the uncertainty, they were equal to 1 divided by 4 of 2n plus 1, which is not surprising, is always greater or equal to 1 divided by 4. And only for the case of vacuum, we are saturating this. All right. And we say that if you look at the x1 and x2, the quadrature, what we are expecting that the uncertainty that we do have, it will be on a circle. What is the dimension? I mean, the uncertainty that we have, this is what we call it delta x1, and this direction we call it delta x2. Okay. And this is the uncertainty that we have for them. If you go, and vacuum is an exceptional case, which is located here. And this is given by 1 divided by 2. And this is given by 1 divided by 2. All right. Then we moved to another case, which was equally, which was with a certain probability distribution for photon number, and we call these coherent states. And we have not done in the way of displacement operator. We have done it in different way. We look for the eigenstate of annihilation operator, and from these we built up the state. But however, the coherent state of alpha also can be built up based on the displacement operator acting on vacuum. So essentially what you do in the quadrature space or phase space, you take vacuum, which has minimum uncertainty, and you displace it to any direction that you wish. So for example, you can displace it here. And then you have a new state, which we call it coherent state. And we will do the calculation, and I think we have done the calculation. We calculated the delta x1, which was 1 divided by 4, with the 1 divided by 2, and we did the calculation for delta x2 as well, which was 1 divided by 2. So for coherent state, delta x1 times delta x2 was 1 divided by 4, which is saturated, saturating the uncertainty for the quadrature of x1 and x2. All right. And for this specific state of coherent state, essentially, if we do the expansions, we found that expansion in terms of photon number state was given by summation of alpha power of n divided by square root of n factorial n times the photon state of n, which is changing from 0 to infinity. All right. We look at the average photon number of n, and what we found that average photon number of n was equal to square root of alpha, if I remember well. Sorry, reverse, was alpha square. Okay, yes, that's true, because if you do A dagger A, and that will give you this result. So essentially, the radius that we had was here was square root of alpha, which is essentially is given by the value. I mean, you can do the mathematics. Radius was square root of n. All right. So that was the case for coherent state. And what we found that based on time, and upon the time, the coherent state is start to do rotating in the quadrature space. It exactly look like simple harmonic oscillator. And in the case of simple harmonic oscillators, if you look at X and P, what you will see that X and P, they will be on a specific radius. And for classical, let's call it classical simple harmonic oscillator, if you have X and P, which is look like X1 and X2, the trajectory in the phase space will be on a circle which is rotating. And this circle is given by the Hamiltonian. You can look at the Hamiltonian, you will find out. Okay, and upon the time, you can find it at any given point here. But that is a very sharp line. Essentially, what does it mean? It doesn't have uncertainty. So essentially, it can be as small as you wish. All right. So that was for the case of coherent state. Good. We had another state, which we call it squeeze coherent state. Okay. And squeeze coherent state was built up based on acting a new operator on vacuum. And what was this new operator? Essentially, people, they have different definitions. I mean, you can go with definition of Scully, or you can go with the definition of other books, but essentially is taking the squeeze operator acting on a coherent state of alpha. Okay. Remember, alpha was a displacement operator, which was exponential of alpha A dagger minus alpha star A. All right. Squeeze operator instead was not a linear, but was a quadrature one, which was exponential of, I think the first term was A. It was, if I remember, yes, was zeta 1 divided by 2, zeta star A operator power of 2 minus zeta A dagger power of 2. Okay. All right. And I remember that Manuel asked me that, Ibrahim, can I write this as displacement operator acting on S operator? Can I commute them? Okay. And I say to him, go at home and do it. What was the result, Manuel?
I didn't have time, but they don't commute, I'm sure.
They don't commute. So who can confirm this?
The book.
Whom?
The book, Scully.
It was not in the book of Scully.
Oh.
You do have, sometimes you do have really wrong references, Manuel. You say to me that Casimir effect is in the book of Steve Barnett, but I looked the entire of the book, I couldn't find anything. Anyway, so let's do this. I mean, it is interesting to understand really that you can commute them together or you cannot that. So assuming that you have S operator, which is a squeezing operator, acting on the alpha. And by the way, remember that zeta, which is the squeezing operator, squeezing parameter, is a complex quantity. So essentially, it can be written as r e power of I theta, which r is the magnitude of squeezing. Okay. And remember, r and theta, they are elements of real quantity. So it's not necessary that they are a complex one, okay? So if you have a squeezing operator acting on a displacement operator, and the question is that can we write it in terms of displacement operator acting on squeezing? Okay. Let's do that. We can do S of zeta, D of alpha. We can insert okay. We can insert an identity here. So it means that you have S of sigma D of alpha, S dagger, or -1 of theta, S of theta. Okay. Do you understand what I'm doing? I'm adding identity here. These can be calculated. What is S acting on D and S minus? Essentially, that is given by D of certain quantity. I call it gamma, S of zeta. Okay, which D of gamma is equal to, or set to be S of zeta acting on D of alpha, S of -1 zeta. So if you pay attention, I have introduced a new parameter of gamma. Is not expanded in terms of alpha and zeta. And if you do a little bit of mathematics, you can expand gamma essentially in terms of alpha and zeta. And in terms of the parameters that you do have, and essentially gamma is given by alpha cosine hyperbolic of R, which is R is the magnitude of squeezing, plus alpha star e power of I theta, and that should be sine hyperbolic of R. Check for the sign. I don't remember really the sign. It should be positive or should be negative, but essentially is a rotation in basis of R. Okay. So Manuel, that's your answer. Essentially, yes, you can do, but now the squeezing parameters and the displacement parameter is changed to a new quantity. Okay, but the proper answer is no, you cannot do that. However, if you wish to do so, then you have to be careful which parameters you are going to use. So for squeezing or squeeze coherent state, and by the way, you can do squeeze vacuum as well. So there is no displacement essentially. Alpha is set to be 0. You can do whatever you wish. So if you look at the uncertainty principle for the squeeze state, essentially delta x1 and delta x2, what you will get that is given by 1 divided by 4 e power of minus 2r, and the other one is, of course, power of 2. And that is given by 1 divided by 4 e power of 2r. All right. So if you look at the uncertainty principle, delta x1, delta x2 is given by 1 divided by 4, which essentially is the property of vacuum state, okay? So it seems that the area is fixed. However, what is happening, if you plot them, you will see that along x1, the state has uncertainty, which is reduced by this parameter. Okay, which is exponential of minus 2r. What is the magnitude of squeezing that you do? If r is equal to 1, then you reduce it to 1 divided by e power of 1 divided by e, which is 1 divided by e is 0.3. Essentially, you are reducing that, let's say, uncertainty that you do have it here, assuming that is a coherent, by the way, this is the squeeze coherent state. You reduce it to from 1 divided by 4, 1 divided by 2 to 1 divided by 2 times 1 divided by e. So you reduce it further. While along y or x2, essentially that will be expanded such a way that the area is fixed. So it will be like this. Okay, so this side is reduced to be 1 divided by 2 e power of minus r, while in that direction, it is expanded. It is 1 divided by 2 e power of r. And we call these squeezed along x1 direction. Along x, you are beyond the uncertainty that you expect. But along y, or let's say x2, you are expanding the uncertainty. But you are not violating it. Remember that. Will be at the origin. It will be like this. It is squeezed vacuum state. And again, this is delta x1, and this is delta x2. Okay. And upon the time that will be rotated. But anyway, what you will get as a field, if you remember, this was time and this was the field, or photon number state, if you want to call it in this way. For vacuum, essentially what you have something like that. erase the upper one. Okay. This is for the case of vacuum. The noise or uncertainty that you have it is fixed, is given by 1 divided by 4. Or let's call it 1 divided by 2. While if you go for the case of coherent state, case of coherent state, this is for vacuum. You do have the oscillation, but this oscillation has an uncertainty, which is expanding from certain value, coming to a certain value. Okay, which this uncertainty is given by 1 divided by 2. Again, what is happening for the case of squeeze state? Well, let's go simple, squeezed vacuum. Previously, vacuum was like this, and now what you expect? Again, that range will have oscillation, but sometimes this oscillation has a minimum amplitude. So it goes slightly like that. Okay. By the way, don't forget that intentionally I'm doing some tricks here. Okay. It will be corrected. If there is any mistake for the next lecture, I will tell you in the video. So don't trust to what I'm writing here. Okay, so this is what happens for squeeze vacuum. Essentially, in some places it gets minimum value. In some places it will be expanded beyond the range that you had it, by the way. Not necessarily in the range, it goes higher. Okay, the same story here. So this is the noise or uncertainty that you have it. At a certain given time, then you will have a minimum minimum uncertainty for one of the quadratures. So this is what we call it. So it can be for phase or it can be for amplitude. That's what we call is squeeze amplitude or squeeze phase. All right. Okay. All right. I will give you a hint. Draw these for the next lecture. Okay. All right. So now with this, let's say, scenario and understanding what's going on with the uncertainty principle in the quadrature space, I think we are ready to move on and look at the probability distribution. So far, what we look at them, just look at the delta x1, delta x2. We did not look at what is the distribution of the state, okay? And this is extremely important. And before going there, also there are some other states which they can be useful. So one of them is what we call it photon number added coherent state, because you can have a coherent state acting on any photon number, okay? You can do that, and this is what we call it alpha and n.
I call it n.
Pardon?
No, it's okay.
Was any problem? Okay. So, for example, if you can have state of alpha and 1, which is single photon added coherent state, this is very important. Okay. Added coherent state. How you can add one photon to the coherent state, and you change the probability distribution. I think that was experimentally observed and created in the lab in maybe 2000, and it was maybe a Science or Nature paper. And so it has some specific metrology feature. So just to tell you that you can do whatever you wish for any states that you want. So, all right, we are now ready to do to look at the probability, look at the statistic, look at the way that this distribution is plotted in the phase space. So before doing so, let's review what is the probability essentially in the quantum mechanical language or in the classical way. So essentially, I think I have specific notation which I want to stay with my notation and not changing too much. So essentially, you can have a probability distribution which is given by P along X. And that is probability distribution. X can be bounded or can be unbounded. It's up to you. It can go from -infinity to +infinity, or it can be between 0 and 1, or it can be between 1 and -1. And we know that the probability is normalized. So is equal to 1. We assume that it's unbounded. And we can come back to this and how in quantum mechanics we assign the probability to a specific state, which is given by amplitude square modulus of the wave function. But also it is good to know that we do have, for this probability distribution, we do have another useful function, which is what we call it characteristic function. And this characteristic function is essentially Fourier transform of the probability. So essentially, if you have a probability of Px, do the Fourier transform. Yeah, let's do it in this way. Without the normalization, doesn't need. Dx, Px, and e power of -ixy. Then essentially I will get what I call it characteristic function. And this characteristic function is essentially important when it comes to the language of quantum mechanics. You will see it in next lecture. I don't believe that we can talk about that this lecture. It requires a lot of time. Okay. And can someone tell me if I want to look at the, let's say, expectation value of certain, let's say, quantity. The quantity that I have is quantity of O. And definitely this quantity of O is a function of X because it has a certain functionality on X. Can someone tell me what is the expectation value of O?
The integral of OX px?
Integral of O px dx, or essentially, let's be a little bit careful with the notation that we use. Integral of OX px dx from -infinity to +infinity. Okay. Can someone tell me, explain to me that Cy essentially is integral of dx e power of minus I xy px, all right? What is this characteristic function? Look at these two, compare this equation and that equation.
It's the expectation value of e to the power minus ixy, the function.
Exactly. Ixy, expectation value. Okay? There's nothing more than looking at that function and finding the expectation value, or the average, if you wish to call it. So characteristic function is essentially nothing more than looking at e power of I x times a function, a variable, and looking for the expectation value of that. Hey guys, don't get lost, because why we are doing that? So far, we understand the field quantization. So far, we understand what is annihilation creation operator. We understand that we can have different states. We can understand, we can build up different states. And we know that how to minimize and deal with uncertainty principle of them. Hereafter, what we want to do, we want to look at expectation values of certain operators for those cases, for those states. We want to understand how to deal with physics of those specific states, okay? And before doing so, we want to understand how to build up the probability distribution. All right, why I'm talking about characteristic function. The first thing that you get as a function in quantum mechanics or any other things is what? Because they are functions, right?
The wave function.
Wave function, well, let's call it wave function, or what you deal with usually. What are those operators? Do you understand what I'm saying? So, for example, I have an operator, observer, observable of A, or O, operator of O. What is the form of O?
Like a matrix?
Maybe. Go back. Okay, so I'm asking you, in matrix, in which basis? The first thing that you should ask yourself is in which basis I'm working on, right? So, Kate, tell me one interesting physical property that you want to observe.
Of what?
Anything. I mean, if we have a physical system, we want to observe a certain, let's say, observable.
Energy.
Energy. Okay. What is energy? You just learn, right?
Yeah. I mean, in terms of
energy is given in terms of A dagger A, right?
Yeah, yeah.
All right. Do you agree, guys, on this? Okay. Or if you don't like this formalism, you can go and look at the Hamiltonian-Jacobi equation. And what you will get, that energy is given in terms of P squared plus M squared omega squared Q squared. So essentially it's given in terms of P and P squared and Q squared, right? So now I'm repeating my question. What is the first thing that usually you deal with? Are you dealing with exponential functions? Are you dealing with polynomial functions? Or what? Because now we deal with operators of A and A dagger, or we deal with P squared and Q squared. So essentially what we deal usually with is polynomials of operators that you want to calculate. So Kate could have asked me that, no, I'm interested to measure position. So I want to measure X, or I'm interested to measure momentum, which is P, or kinetic energy, which is P squared divided by 2M. Okay, or anything else, angular momentum. So any operator that you do have is essentially, if it, I mean, those standard things, they are polynomial series. So here, what we are dealing with usually in the probability calculation, we are dealing with something like that, integral of dx of px, some operator, which is polynomial. Let's say polynomial of x power of n. All right. This is the reason that people like to deal with characteristic function of y. All right. So what I'm interested in, I want to calculate what is the average of x power of n, which is essentially this. How do you do the calculation? Eric? I'm interested to calculate integral of dx x power of n px. And the only things that I know is that the characteristic function is this.
Take the
yes,
you can calculate the characteristic function or take the integral over y as well of this of e to the minus ixy, and then take the integral over y and then see what happens.
Okay, let me do okay, so we have a cy, which is integral of dx px in e power of minus I yx. Take the derivative with respect to minus iy, right? Of cy, what you will get?
Get x times,
exactly.
You get the expectation value of x, yeah.
Exactly, you will get x, p, x, e power of minus I, yx. Do you agree? Take n derivatives, n time derivatives of these with respect to minus I, y of cy. Then you will get dx, x power of n, px, e power of minus I, yx. Clear? Now, evaluate this at y equal to 0. What you will get? I will get derivative of n with respect to iy and cy equal to integral of dx at y equal to 0, x power of n px. This is exactly what I was looking for. And that's one of the reasons that people, they prefer to work with the characteristic function, because it is easy to do the Fourier transform. Then what you need, just dealing not with integrals, but taking the derivatives of that. Okay, then that is given by iy power of n. With respect to negative sign, by the way, this should be negative sign, of cy at y equal to 0. Are you familiar with multivariables probability distribution? You can have x1, x2, x3, x5, xn, this is n-dimensional probability distribution. In the same fashion, you know that integral, you can have a probability distribution which is function of vector of x, essentially, which vector of x is x1, x2, xn, which is n dimension. Then the probability distribution that you do have is integral of dn of x, p of x equal to 1. And in the same fashion, you can define another conjugate space, which is y1, y2, and yn. And again, you can define a characteristic function for that n-dimensional probability, which is given by integral of dn of x, px, e power of minus I, x dot y. Okay. In a similar fashion, the probability distribution for x1 power of n1, x2 power of n2, x3 power of, xn power of nn, average of these is given by derivative with respect to n1 of minus I y1 of n1, partial derivative with respect to n2 of minus I y2 n2 nn, partial derivative of minus I yn and n of cy. And at y equal to 0. And what we know is that minus I yn and n, the characteristic function essentially is nothing more than the average of the Fourier transform. This is what Nazanin told us. So essentially, this is e power of minus I x dot y average at y equal to 0. So essentially, if you deal with probability distribution, and for this specific probability distribution, you can build up a characteristic function, and you can almost do any polynomials observables for that specific probability distribution. Okay, so for example, if px is Poissonian distribution or Gaussian distribution that you have it along specific axis, so let's call it p is exponential of minus x squared. So for example, if px is e power of minus x squared, which is a Gaussian distribution, of course you do need 1 divided by square root of pi, if I remember well. So you have to do a little bit of mathematics. I think that should be the normalization factor. Then if I want to ask you, what is the characteristic function of this? Can someone tell me?
Another Gaussian.
Exactly. It should be a Gaussian. With a different coefficient, of course. You have to find the coefficient. So that's the characteristic function. So for probability distribution, which is Gaussian, it is easy because the characteristic function, again, is Gaussian. But you can do any, you can do the mathematics and find any average for any probability, any observables. All right, is it clear? Good. You need that because at the end of this, when we get to Wigner representation or Wigner functions, you will see that is essentially nothing more than this. And it's just borrowed from classical probability distribution. Is not really surprising. Okay, so don't forget that because we will need them for next lecture. I was hoping that we can finish today, but it's very unlikely because we have almost 1 hour left, I think. Sorry, 1 hour and 20 minutes left for the lecture. But we will definitely touch these. Okay, so now we know the classical probability distribution, and we are familiar, or we get familiar with a characteristic function. Now let's go on and go to quantum mechanical picture. In quantum mechanics, for a pure state, of psi, if you have an operator of O, how do you find the expectation value or average of O? Felix?
You can just integrate over all space with O and the state. Or if you're using maybe the ket form, then we just go with the ket. Yeah, exactly. So okay. A ket on either side of the operator.
Lovely. This is exactly the expectation value that you have it from the quantum mechanical one. Okay. So for example, if O is an operator which projects on a specific state of P, so O project on specific state of O, let's call it. Okay, and is diagonalizing the space, okay? Then expectation value of O essentially is projecting on that state square modulus. All right. It looks like finding the projection along that specific vector and making the square modulus, finding the amplitude and finding then the probability, which is the square modulus. It is not surprising. So this is essentially what we have it for any observables of O, okay? Or any operator of O. Fine. And you got familiar also with the probability distribution in X space, which we call it usually psi of X, right? I mean, this is what the quantum mechanics was built up based on this. And then you look at the integral and you say that should be normalized to 1. Okay, I don't want to talk about this. This is, I think, by definition, you all know. However, in some cases, we don't deal with a pure state, or in most of the cases, essentially, we don't deal with pure state. What we deal with is a mixed state. What does it mean, mix? So, for example, I will give you a photon in photon number of 1, okay? So Arman will be the person that receives this, and Arman doesn't know what I'm doing. In the first shot, Arman will receive one photon with amplitude of, let's say, 1. Okay? Then, second time, I'm sending Arman a specific state which is in superposition of 1 and 2, okay, with equal probability, which is 50-50, but is coherent superposition of 1 and 2. Second time, I'm sending Arman another one which is in with 100% in the state of 2, okay, and etc. So at the end, Arman has a set of ensembles of the state after n trial. He will get, let's say, an ensemble of the state. Which, if all of those ensembles they're identical, then this is what we call it, is a mixed state. Not necessarily, let's put it in this way. It is mixed, it is a pure state in a naive way, because there are some cases which also the states are identical, but essentially if you trace over, then it will be a partially mixed or fully mixed state. But for the time being, assume that we have a state, which I'm sharing with you. So if all of them, they are identical, then is a pure state. If psi1 and until psi n, they have some changes, then you deal with ensemble, and not necessarily that you will have a pure state. But you know what is the probability of each. Probability is known to you. So in the same fashion, what I can do, I can take the operator of O, doing average for each of those states, which is essentially is nothing more than psi I, O psi I. But now, doing average for the entire set, for the entire set of psi j, we will do the average, okay? So it means that the operator of O should be average over ensemble, or the ensemble, okay? Then what we do, we know that each of them has a certain probability distribution, or it's probability of pi, or p yeah, let's call it I. And then we do have psi I, O psi I. Okay? No surprise that all probabilities should be equal to 1.
So just to confirm here, so when you have a mixed state, it's basically like you did like n measurements here, and you were able to determine the state of each of those n measurements, but you don't quite have enough information to put it into a pure state formation.
Let's elaborate it a little bit more, okay?
Okay.
Josh, you are the observer, okay? And you have observables that you want to measure. What are you comfortable with? Polarization of light?
Sure.
Okay, fantastic. So you have a device, or you have a set of measurements that you can perform the polarization measurements. You don't know what I'm creating, right? Remember, it's an arbitrary situation that I'm sending to you. I'm sending you, let's say, 100 states, right? The first one is H. Second one is V. Third one is A. Fourth one is D, okay? And etc. I'm repeating that and sending to you. What do you end up at the end? you have different states of H, V, right?
Right.
A, D. What are the probabilities of all of them? Equal probability that I'm sending you, right? At the end, what you end up, it's a mixed state. You don't know really what is the state. It's totally a mixed state, which is, if you do the mathematics, you will find out that it is, let's say, 50% in H, 50% in V, because those are the two, let's say, independent vectors that you have. Okay, but you can perform any measurement that you wish on that 100 ensembles. You will get an answer for this, which is that operator of O that you perform the measurement. And you know also what is the probability of them. You can sum them up together. And at the end, what you have the expectation value of operator O on the ensemble that I provided you. Clear?
Yeah, I think so. Yeah.
Oh, good, excellent. Good. Maybe it was better that we write that as a P of psi I, and I is changing from 1 to n. Good? No problem? No. Okay, excellent. Operator O can be diagonalized in specific base. Okay, let's diagonalize. Let us O. In which bases? In base of n or whatever that you wish you want to call it. Okay. Or even before that, we can do it in any basis that you wish. So for example, we know that photon number of n is complete base. Then we can add an identity here and expand it. So then you have P of psi I, operator of O, n psi I. But remember that we need a summation for n, which is changing from 0 to infinity. All right, what I have done, I just add an identity here. Let's cast them properly. It will be summation of n from 0 to infinity. Then this is now a scalar. I can move the scalar around. I can bring it to the other side. So it will be n summation of I from 1 to n P psi I of psi I O operator acting on n. Do you agree? What I have written here? Good. What is this?
It's rho, the density matrix.
Exactly. This is the density matrix of the ensemble that you had it. So essentially, that will be summation of n from 0 to infinity of n rho of O acting on n. Can someone simplify this further?
It's trace of rho O.
Trace of rho O. So essentially, it looks like having 0 rho O, 0. The rest is, I don't care. 1, rho O, 1. This is in photon number. 2, rho O, 2. And n, rho O, n. And what we are looking for, we are looking at the summation of all of them together. And summation of all of them together is the trace of rho O. And this trace can be done in any basis that you feel comfortable that O is diagonalized. Okay? Good. Clear? Fantastic. So now in the quantum mechanical language, we prefer to look for an operator of O, and this is the expectation value. Expectation value of operator O. And the only things that we needed to do is look at the trace of rho O. Good. That's all. Whether do you want to look at the trace? It's up to you. But it is good to know rho and O operator in such a way that by knowing the properties of rho and O, we can find out that this trace can be written in much easier way. Okay, that's a goal. And whatever that we deal here after is we are talking about ways to compute this in an easy way. Okay, let's look at the naive way. I mean, without again going into deep mathematics, look at the naive way. Okay, so the most trivial things that you want to find this expectation value of O, what is the naive way? In which basis I can calculate that? How many bases did we learn? Because we have to do the calculation, find out the trace, right? And the trace should be done in specific base, right?
Naively, the number state basis.
Let's do it in a number state basis. Why not you do that? Okay, let's do that and find out what is rho. But essentially what we want to do, find out rho in the number base. Manuel, can you do that, please? Write it in a paper, just having an exercise and doing a little bit of sport.
A minute.
All right. What I have done, I just expanded in terms of a number basis. So I had one on each side, and then I did the expansion. Then what you will get, that you will get a density matrix here in terms of photon numbers of n and m. If it is diagonalized, it is perfect. That's fantastic. Here you go. You are done. For example, for thermal light, is this diagonalized? Yes, it is diagonalized. For thermal light, we will also derive this. For thermal light, I think you have done as well. So rho, m, and n can be calculated. Okay. Let's go further. What are the other bases that you can do the expansion?
Coherent state.
Lovely. Let's do that. So take the density matrix and expand it in terms of coherent state. Do that, please. Just to give you a hint for coherent state, if you don't remember, that was the completeness relation. Alpha is changing from minus infinity to plus infinity. Okay, let's do that together. So again, the same fashion. In the same fashion, we can write rho as 1 times rho 1. That will be 1 divided by pi square, integral of d to alpha, integral of d to beta. Then for that one will be alpha alpha of rho. That one will be beta beta. Okay. So there is a quantity which we care about is d to alpha, integral of d to beta, and that is alpha rho beta, alpha beta. So this is the density matrix representation in the coherent basis. However, people, I mean, like Glauber, he used this representation and he preferred to write it in a different form. So instead of this, he wrote that is a function of alpha. I think the things that he used, since alpha was on the broad side, he used alpha star and beta. And then he expanded in terms of minus, I think, minus 1/2 of alpha squared plus beta squared. Okay, so then he defined a new function, which we will discuss about that, was 1 divided by pi 2, integral of d to alpha, integral of d to beta. And then he had r alpha star and beta, e power of minus 1/2 of alpha squared plus beta squared of alpha and beta. I think that should be minus sign. If it should be, look like your book. Okay, so that's, I mean, that's a formalism that you do have it. So people, they have different representation for this. Remember, the goal was finding O operator, which is trace of rho O. And as we discuss, and we will see it in a couple of minutes, we do have different way to show this. I mean, we already seen that you can do the expansion in terms of photon number basis, or you can do it in terms of coherent state. And you already see that in terms of coherent state, is look like, it's a little bit complicated, but it's interesting. Okay. Why not having a break? And then we will come back. Let's say that at 4:10, we will be back and we will continue with super operators. So I have to define super operators, and then from these, we will get P, Q, and W representation. All right? Any question? So far, it was simple, I think. Okay, I will stop recording. And at 4:10, we will be back and we will discuss. So we looked into the possibility of finding the expectation value for O operator. And it ended up to be the trace of the density matrix times O. Okay? So far, I think everything is clear. Now we should look at the possibility that we can simply understand what is O operator, or what is the value of this, which means that how can we diagonalize O operator, and how can we diagonalize also rho operator. So that's really the goal. So we looked at the two cases which we have a coherent states representation. You can look at that, or you can look at the photon number state, which is another possibility. All right. Now I'm telling you, again, the same question which I asked Kate, and she replied to me. So what I'm expecting O operator to be look like is function of what? Anyone can reply if you have any thoughts.
Of the Quadrature annihilation?
Yeah, essentially is a function of X and P, which for us is look like function of X1 and X2, or is annihilation operator and creation operator. Okay, I think we discussed that we are working in the single mode base, so that's clear. You had the assignments which was deal with multi-mode squeezing and other things, so I'm sure that it's very clear for you that what we are doing. Clear? Good. Tell me one case. Let's say, gosh, any volunteer? Tell me an operator that you want to measure.
Number operator?
Number operator, N. What is number operator? Is A dagger A. All right, easy, too easy. What else? is an example.
Spin.
We did not write the spin in that proper language, sorry. But you are right, you can build up a Hilbert space for that and just expanding that. Yeah. Even special mode is the same scenario. So we are only dealing right now with photon numbers. Remember that when I think those people, they work in my group, we translate everything in terms of spatial modes. So we deal with the case that in maximum we have 1 photon, so 2 photons, not more than that. And when we do as a Hilbert space, we deal with a spatial mode. But here we deal only with photon numbers. 0, which is vacuum, 1 photon, 2 photons, 3 photons, and etc. So what else? Arman, do you have any thoughts? So something else, tell me. You're muted. Sorry.
Sorry. I mean, it could be the quadrature operators themselves.
Which involves n square?
Sure.
This is the quadrature of n, let's call it, right? So what does it mean, n? It has a dagger a power of 2, which means that you have a dagger a times a dagger a. True? Can I calculate this easily? No, right? Because usually I know that in the coherent basis, I have to have all A's on the right side and all A daggers on the left side, because that's easy for me to do the calculation. So what I have to do, I have to rewrite this as A dagger A dagger A, which is, if I want to do this, I mean just A dagger, then that is A dagger A plus 1, which is A dagger A plus A dagger A. True? That's another operator that I can look for the expectation value. Or Arman said something else. You mentioned quadrature, x1, right? Which is A plus A dagger divided by 2. Or I can look at the x1 power of 2, which is A plus A dagger divided by 2 power of 2. Guys, sometimes I forget to place hat. Just accept that this is an operator. When I don't want to write the operator, I will write it in terms of alpha and alpha star. So that's the, let's say, the value. If I don't have a hat operator, just assume that this is an operator. So this is 1 divided by 4 of A plus A dagger times A plus A dagger, which is 1 divided by 4. Why I'm doing that? Because I want you to understand and feel that there is something important that you have to take care of it, okay? So that should be A plus A dagger plus A dagger A plus A dagger power of 2. Huh, cool, that's beautiful. Let's write that one in this way. A power of 2. Good, lovely. What else can I write this? So the same expression, I can swap, not this one, maybe that one, because this is a problem for us. We cannot easily calculate it because all A dagger should be on the left side. So replace this with A dagger A plus 1. Then what we will get 1 divided by 4, A squared plus 2A dagger A plus A dagger power of 2 plus 1. Or I can write it as a 1 divided by 4 a squared. A dagger minus a dagger a is equal to 1. So if I want to find a dagger a, it is a dagger with a minus sign, plus sign minus 1. Okay, so that should be plus 2a dagger plus a dagger power of 2 minus 1. True? So if you look at the x1 square, I have 3 ways to show it to people. What are those 3 ways? One is, this is the same, all of them, is 1 divided by 4 a2 plus a dagger plus a dagger a plus a dagger power of 2, which is symmetric way. Whatever you have it between a and a dagger is symmetric, right? Or I can write it in a way that is ordered. In which way? In a normal way that we have. So it can be a power of 2 plus 2a dagger a plus a dagger power of 2 plus 1, which is normal order. What I mean by normal order, a dagger is on left and a is on right. Okay. Then the same operator also can be written, oh, sorry, that's 4, 1 divided by 4 of a power of 2 plus 2a dagger plus a dagger power of 2 plus 1. Sorry, minus 1, which is anti, you know, normal order, which in this case, a is acting on left and a dagger is acting on right, okay? Good. The same operator, I have 3 representations for it. It's not look like classical mechanic, which the position of the operators, they are not important, but it's different, okay? So assuming that, I mean, if simply is look like replacing a with alpha and a dagger with alpha star, which is not true, by the way, then easily I will get 3 functions as an outcome. However, depending on the problem, depending on the state, or let's call it in this way, depending on rho, you can use and pick up any of those operators representation. So, can I use this? Of course I can use that. Can I use that one? Yes, of course I can use this as well, or the other one. So it's 3 different representations, all identical. But which one is easy? That depends on rho that you have. Rho will define which one will be used in your calculation, okay? And that's the big message that you have to, and the main message that you should receive. So first one, which is symmetric way, we will talk about that. Normal one, we will talk about that. And anti-normal one, also we'll talk about that. And we will say that associated to them, to those, let's say, way, we do have 3 ways of plotting the density matrix. Remember, O operator should be calculated as a trace of rho times the operator of O. So you are not only dealing with O, but also you are dealing with rho. These 2, they are important. Rho will tell you what it should be, the presentation or representation for O. And then easily you can do the trace. Clear? Henry? Clear? Excellent. So essentially, if I want to look at the, and by the way, this average or expectation value is or the sample state, depending really on your problem. O essentially is a function of A and A dagger. In our calculation, by the way, if you deal with spin, that will be a different operators. If you deal with spatial mode, different operators. But for us, we are dealing with photonic statistic, photon statistic, which is numbers. We are dealing with A and A dagger. And I will put a symbol of sigma, okay? We will talk about sigma. What do you make a guess? Sigma should be associated to what? Do you have any feeling?
Variance, maybe?
What?
Maybe the variance of the variable?
No. Associated to any of those three cases.
The symmetric one?
It can be symmetric, normal, or anti-normal. So the value that we have it for sigma, it is three different values, depending on the choice that you have. Okay? We will discuss about that. But just remember that this sigma tells us about the way that you arrange operator, A and A dagger, let's call it in this way. Okay? And this is trace of rho and operator of A and A dagger. All right? But however, I'm writing the formula just directly here, and the entire of the lecture will be about driving this formula. Integral of d2 alpha w of minus sigma of alpha operator of sigma. Okay. So we want to find the expectation value. And the expectation value for any way that you want to order it, the operator that you want to order it, will be associated to opposite order of probability distribution. This is important. You don't get it in books. Okay? Any way that you arrange the operators, being ordered, anti-ordered, or symmetric way, you have to use the opposite one on the probability distribution. Okay?
And that guarantees you get the same result?
Pardon?
Does that guarantee that you get the same result?
Yes.
Okay.
Yes, right. Indeed. But remember that in some cases, it is extremely simple to do the calculation. And we are fighting for that we could do the calculation in some cases easier, right? And remember, we call these quasi probability distribution. It reminds you of something, right, guys? Alpha is a complex quantity. Do you remember that? It's a coherent, it looks like the parameter in coherent state. It has a phase, it has a magnitude. And you're doing the integral on complex plane, which is D2 alpha, right? Do you remember the classical one? We just described that in the classical way. Let's go back, go back, go back. Do you remember this classical one? Right? This is a classical probability that we had. What we have written is similar. The only thing that is changed is that P is replaced by W, and X is changed to be in two-dimensional way. You can call it, usually people, they go with real part and imaginary part, or you can go with alpha and alpha star, or you can go with X and P or X1 and X2. It's really up to you. It's whatever you feel more comfortable. But what is important that you are trying to link the expectation value of an operator to a probability distribution in the classical way. And you have a name for this W, which is P, look like the classical one, and we call this quasi-probability distribution. Why we call it quasi-probability distribution? Because for some cases, it has a negative value. It's not always positive, okay? Let's go back. Good. Excellent. Huh. Now our job is just finding this. Now I'm doing the mathematics, but don't get lost in the calculation. The goal is clear. This is your goal. This is what you do entirely. Finding O operator in the sigma order, sigma either symmetric, antisymmetric, or anti-normal or normal. And then associated to each of them, you do have a probability distribution, which is either probability distribution in the base of symmetric, anti-symmetric, or anti-normal or normal order. And now we prove that for the calculation. Good? This is important because hereafter I'm doing only mathematics. I'm defining many crazy things, but just remember this is the message. All right, let's go and do the mathematics. So operator O that we had, operator O that we have, which is A and A dagger, it can be expanded in normal order. What do I mean by normal order? It means that can be expanded in polynomial basis. Essentially, this is what I define for a characteristic function, because also characteristic function will show up in some cases for our scenario, and I call it S of M and N, A dagger of M, A of N. All right. M and N they are changing from 0 to infinity. Since this is a normal order, I assign a number to it, and this number is 1. Remember, for normal order, sigma is equal to 1. It's the one that I define. In the same way, O of A and A dagger, anti-normal order. What I do here, I will swap the operators. I assume that I'm able to do all of those commutations, substitution, and then I will end up with S of M and N, A of N, A dagger of M. Here, sigma is -1. For anti-normal, sigma is said to be -1. Good. For symmetric way, it is easy. Symmetric ordering is summation of M and N changing from 0 to infinity, S of M and N, A dagger of M, A of N. I use this as symmetric. I'm telling that by having a curly bracket here, that this is arranged in a symmetric formalism, which it means that I have to look at all permutations between A and A dagger. So we can have an explicit expression for that. And for symmetric order, sigma is said to be 0. So I will label it with 0.
How do you know you can always get a symmetric ordering for an operator?
You can always do that for a while group.
Oh, okay. It's because of the way that A and A dagger commute?
Yes.
Okay. Awesome.
Always you can replace either way, and then at the end you will you can make it symmetric way, or you can move it in the other way. If you wish, you can prove that. I think I don't remember the first author, but Glauber was the senior author that they proved that. So as an exercise, you can do that. Okay.
Do we write this symmetric as just A dagger to the M, AN plus AN, A dagger to the M?
Symmetric means like that.
Yeah. So sorry, and just in the summation, would it be sufficient to just like flip, like do plus A to the, like just flip them and have two terms?
Oh, yeah, you mean like that. So for example, if I have A3, A dagger, then yes, you can have it A dagger 3, A.
Yeah, okay.
Okay.
Yeah.
And always there is a possibility that you can do that. And essentially, if I want to have the symmetric way, this is the symmetric way of A dagger power of M and A of N. That's a symmetric way. Symmetric. That is 1 divided by permutation of M plus N out of M. And then you have a summation of all permutations. This was your question.
Yeah.
Permutation of a dagger power of M and A power of N. Okay. And I know that it is bonded between M and N, so just be careful with the summations. Good. Essentially, now for all of these 3 ways of representation, I have single one. I say that O of A and A dagger of sigma, this is the sigma that we discussed about that previously, can be written as summation of M and N changing from 0 to infinity, S of sigma of M and N, A dagger M, A N in the order of sigma. Okay? So if sigma is normal order, then you have to swap them. If sigma is anti-normal, then you have to go with other way. If sigma is 0, then is symmetric way, then you have to make it symmetric. Clear? I think you got the point why this is important, that we have to work for order and normal order or anti-normal order. Okay. Good. As an example, this can be a displacement operator of alpha. Oh, let's call it beta. I don't want to deal with alpha that we have previously written. What was the displacement operator of beta? E power of beta star A minus beta A dagger. Right? Oh, sorry, it's reverse. Two. How can we make it normal orders or anti-normal order or symmetric way? Any thoughts?
You expand it first.
Okay, let's do the expansion. It's summation of beta A dagger minus beta star A power of n divided by n factorial n is changing from 0 to infinity. Okay. This is one way.
You could write it as that, as the formula with the product of 3 exponentials.
Exactly. That's
one of
another
them is
way.
the exponential of the commutator, which is just a scalar in this case, and then you can pick the order of the exponential of the annihilation and the exponential of the creation, depending on the sign of the first.
Lovely. So let's go first with what Eric's and what Josh mentioned, and then we will go with what Eric mentioned. Okay. So if you do the expansions, let's go with that. So the first one, it will be power of 0, which is 1. Second one is power of 1, which is beta A dagger minus beta star A divided by 1 factorial. Is that symmetric? Yes, it is symmetric. I don't care about beta and all beta star. That's a different scenario. Look at the other one. 1 divided by 2 factorial. I get beta A dagger minus beta star A times beta A dagger minus beta star A. Is that symmetric? Yes, I can expand it and I can make it completely symmetric. Fine. So this way of expansions will give me the symmetric way.
I'm not sure why it's symmetric, because the first one, there's different coefficients on A and A dagger.
Oh, you can make it. You can make it symmetric. I got your point.
Okay.
I got your point, but you can make it symmetric. The second one, which what you mentioned, Eric, I mean, expanding these e power of beta a dagger minus beta star a, going from e power of a plus b was, I think, one of your assignments, to the other space, which is, it was e power of 1/2, I think with negative sign, of a and b. Then we had e power of a, e power of b, right? It was one of the case of Baker-Hausdorff, Campbell expansions. So we could get e power of, I think that should be minus 1/2 of beta square, or plus, I don't know. Can someone check it out for the, because it's a dagger a, then it should be, yes, negative. Yes, that's true. E power of beta a dagger, e power of minus beta star a. All right. And let's do the expansion, e power of minus 1/2 of beta power of 2. Then that is summation. For the first one, I can do the expansion on n. For the on m, and the second one on n. Then I will get beta power of m minus beta star power of n divided by m factorial n factorial. Then I do have a dagger power of m, a power of n. Right? That's a normal order. So I can find the normal order as well. For the anti-normal, how should I do the mathematics? The same expression, and we got the negative sign, positive sign. So essentially, yes. So for this is for normal order. This is for anti-normal, which is displacement operator e power of beta a dagger minus beta star a is given by e power of 1/2 of beta square, e power of beta star a, e power of, with negative sign, beta a dagger. Okay. This is anti-symmetric, anti-normal order. Good. We can do the expansion. We get e power of 1/2 of beta squared, summation on m and n. I want to have the same indices, so it should be same indices. It should be the same. Beta power of m minus beta star power of n divided by n factorial, n factorial. Then I have a power of n, a dagger power of n. Okay. Good. Questions, guys? Or you're okay? Look at the expression here. This was an operator of O. We can have a coefficient expansion of Sm and plus 1, Sm minus 1, or Sm 0 in terms of annihilation and creation operator. And for displacement operator, we found that. So let's write it down, maybe as 3 ways. I'm doing it only for anti-normal and normal one because it's an explicit expression. For the rest is not. So let's do that. For what we do is displacement operator of beta. Just remember is e power of beta a dagger minus beta star a, which we wrote it as in the normal order. In the normal order, we got summation of e power of minus 1/2 of beta squared of beta m minus beta star n divided by m factorial n factorial, a dagger power of m, a power of n. M is changing from m and n, they are changing from 0 to infinity. And for anti-normal, we got summation of m and n changing from 0 to infinity, e power of 1/2 of beta square, beta power of m minus beta star power of n divided by m factorial n factorial, a power of n, a dagger power of m. So this is, should I call it, for this operator, I will call it d of m n, and that's anti-normal is -1. And this is d m n of +1, which is normal order, okay? People, they have different notations, by the way, just remember. People, they write without exponential, everything is normal order, of course. So people, they write it in terms of d of beta. Without exponential, also they write it anti-normal, which is d of beta. Is a definition. People, they say they don't care about how the operator are set. This means that is summation of beta power of m minus beta star power of n divided by m factorial n factorial, a dagger power of n, a power of n, and that is look like summation of beta m minus beta star n divided by m factorial n factorial, a power of n, a dagger power of m. And this is a notation that you do have. And always there is one way that you can link one of the representation to another one. Always you can look at that, which is, if you look at this expression, is what you will get. Anti-normal can be linked to symmetric one easily. Okay. So means that this is equal to E if is anti-normal will be e power of, sorry, this is normal, e power of plus 1/2 of beta squared linked to symmetric one, d of beta. And that is linked to symmetric one with exponential of minus 1/2 of beta squared of d beta. Good. Now you will see slowly why I'm using sigma. So d of sigma of beta is given by e power of sigma beta squared divided by 2 d of beta. So when I say d0 means that d is a symmetric way. When I say that d is +1, then it means that is normal order. When I say d minus 1 is anti-normal order. And this is the link between the three representations that we do have. Clear?
Does exactly the same formula carry over to every other operator?
Pardon?
Does the same formula? No, it can't.
You can't.
No.
You can't.
What is there something similar for other operators?
Nope. Nope. Why I do that? Because I want to build up super operator now. Okay, guys, don't get lost in the mathematics. Again, what I'm telling you is just the tools that you can get familiar with the mathematics, how to handle them. But the original formula, don't forget that, is this. Is how the expectation value of operator is linked with the quasi-probability distribution. And I want to prove this to you, okay? This is the goal, that we want to do that. We want to show that for sigma plus, W appears as a negative, and we call this Q representation. For sigma equal to -1, that will be linked to W of +1, which is what we call it a global representation. For sigma equal to 0, that will be linked to W0, which we will call it Wigner's representation. But remember, all of these three, you need to handle the operator in a proper way. Okay, we will go there, but just be patient, I'll leave it. Okay, so now that I know that I can expand the operator in terms of anti-normal, normal, or symmetric way, and I always like the simple harmonic oscillator. I don't know why, but I mean, we use it in any problems, any classical or quantum problems. The first set of problems that they will give it to you is simple harmonic oscillator. First of all, I mean, because any forces can be expanded approximately as a harmonic oscillator around an equilibrium situation. Maybe that's logic. And here also, you will see that the displacement operator is look like a plane wave. And which is, if it's look like a plane wave in terms of operators, then you can use it to construct the basis that you are interested in. So let's do and tell you what I mean, assuming that you have a set of displacement operator. I don't care that it's sigma or is not sigma, just call it displacement operator. For the time being, only dealing with symmetric way, okay? So it's the displacement operator that we had. It was d beta, which is exponential of beta A sorry, beta A dagger minus beta star A is the displacement operator that we had. Assume that we have a set of displacement operator. By the way, this is a set. It's not really symmetric representation. It's just a set of operators. What is changed for these operators if they are set? Annihilation, creation operator, they are the same, right? The only parameter is
beta.
Beta. Beta is changing. So you have different set of beta. Is beta continuous variable? Yes, it is. It's two-dimensional real quantity, or is expanded in a complex plane. So remember that beta is a continuous variable. Okay, two-dimensional continuous variable. And from this, what I will do, I will build up the basis that I need to expand any operators in. So let us define super operators. Okay, before even defining the super operators, look at the case, then you can have linear product. Between operators. Huh, it's so funny. I want to take two operators, doing the linear product and get a scalar quantity. Let's call these two operators A and B. And if you use the proper mathematical representation for the operators, then you can have in the Frobenius definition that is given by trace of a dagger B. If you, this is the definition that you do have. If you take a dagger times B and you look at the trace of them, then what you will end up, you will get a scalar quantity. And we call that, we call these linear product between two operators of A and B. All right. Look at the trace of DB. Sorry, look at the linear product of DB, which is the super operator that I have, D beta prime. What is this quantity? It is trace of D dagger beta, D of beta prime. All right. What is D dagger of beta?
The inverse?
Exactly. What does it mean, inverse? Take this operator, right? Take the dagger. What it will change?
Sign on the sign of beta.
The sign of beta. So that will be D of minus beta. All right? Of D of beta prime. I'm looking at the trace of these operator. Can you make a guess? Which basis should I use for the expansion?
Coherent states?
Lovely. Do it in a coherent state basis. And what you will end up? You will end up with a delta function. do that as an exercise. It's not difficult. Why I wrote that is delta power of 2, I meant that, remember, that beta is a complex number. So it's a two-dimensional variable. All right? So it will be delta of beta real minus beta prime real times the delta of beta imaginary minus beta prime imaginary. Remember, the beta is a complex quantity. Okay? Any questions? This operator of d beta, super operator of this set, they are orthogonal, as you see, and they are complete. What I mean by they are complete, that 1 divided by pi, because that normalization factor, I have to take it here. I have to borrow it from here because I have 1 pi. Integral of d to beta. Remember, I have d2, which again, just to remind myself that beta is a complex quantity, of d beta is equal to 1. Pay attention that I'm using just parentheses for the super operator. So parentheses. I have a new set of bracket notation for myself. I think when I was undergraduate student, I had this course in mathematics. Okay. And the dual operator, dual super operator is this one. Good? Fantastic. Now, any operator of O I can expand it in terms of these super operators that I have. So it means that this operator of O essentially can be written in terms of 1. Then, let's say, sorry, it should be on the other side. That means 1 divided by pi, integral of d2 of beta, d of beta, super operator of d beta acting on O operator. Okay, good. What is this? The inner product of two operators, which is what we define is a trace of d dagger beta operator of O. Eric just told us that d dagger beta is equal to d minus beta, which is what we looked into when we want to look for the orthogonality relation. Good. So essentially, indeed, we end up with the following representation of operator O. Is operator O arbitrary? Yes. for any arbitrary operator of O in terms of displacement operator, which is, I think, was one of your questions, guys. So essentially, operator of O now is given in terms of 1 divided by pi integral of d2 beta of exponential, oh, let's just write it in this form because I don't want to make it more complicated, d of beta, and that is trace of d minus beta O operator. Good. So I can expand any operators in terms of displacement operator. Okay, let me ask someone. Kale? Kale? Yeah, okay, good, thank you. So can you tell me, is D the displacement operator, right? Did I write in normal order, symmetric way, or anti-normal? No, it is general. So if I want to look at O operator in any of those forms, the only things that I have to change is writing the displacement in the proper way that I want. So if I want to look at the symmetric way, I have to write it in a symmetric way, and etc. Good. So just remember this one way to expand it in the way that you want, in the anti-symmetric, anti-normal, in the symmetric way, or normal order. Good. Excellent. We can do that. We can just do the expansions and just see what we will get. Any questions? Is clear? Or is getting very complicated a bit mathematics? Good. Is this valid for any operators? Yes. Let's do that for the density matrix operator. So let's do this and write the calculation for the density matrix operator. Let's write it rho. Rho is given by 1 divided by pi integral of d2 beta, displacement operator of beta, trace of d minus beta rho. Good. Good. So let's expand D in any base that you want. Anti-normal, normal, or symmetric way is up to you. Let's do that. So let's write it in terms of M and N. S of, did we use S, guys, or D? We used D, sorry. D.
We used S, I think. And then D for the
use S?
D for the displacement operator.
For the displacement operator?
Oh, I guess, yeah. We use S for the general case.
Yeah, this is for D. Okay.
Okay.
And M and N of sigma, right? And then we have A dagger power of M, A power of N in the sigma order, right? Remember, these in sigma order. We are replacing this here. And let's do a little bit of mathematics again. So we will get 1 divided by pi. Maybe pi, I have to bring it inside. Or should I do that? Let's just write it in this way for the time being. Integral of d2 beta summation of m and n of the sigma of m and n, a dagger power of m, a n and sigma, and remember times the trace of d of minus beta rho. Good. Let us try for symmetric way. Oh, for should we do it for anti-normal or normal? We can do for either. Just I want to make sure that I'm writing it for a proper state. Maybe I had to do something else for the density operator. That's fine. Okay. What I have done there. Okay, let's try. Let's simplify this in coherent state basis. So which means that I have to use the integral 1 divided by pi integral of d2 alpha, alpha. So a dagger, okay. So A and A dagger, they will act on different sides. So these diagonalize, then it will get, we will get 1 divided by pi integral of d2 beta summation of m and n of d sigma m and n of alpha star power of m and alpha power of n of sigma, in that order, because the creation operator and annihilation operator, when they will act on broad state or Ket state, they will give different results. And again, they will get alpha and alpha star, and the summation on that again will be, which this is what we have, d2 of alpha, 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 that is exactly equal to 1 again. And then trace of d of minus beta on rho. Okay, good. I think yes, that's correct. So 1 divided by pi integral of d2 beta. For example, for the case of symmetric way or even anti-symmetric way, what we will get summation of m and n. That was just remember, it was beta power of m minus beta star power of n, beta power of m minus beta star power of n divided by n factorial m factorial. Then that summation, now there is no symmetric way or anti-symmetric way, anti-normal way, because they are not operator anymore. They are just variables. So essentially that results in the same way. So it is alpha star m alpha power of n. Then we will get alpha star power of m alpha power of n. Then we do have the trace of d minus beta operator of rho. Good. That's 1 divided by pi, integral of d2 beta, summation of m, n, and that is alpha star beta power of m minus alpha beta star power of n divided by n factorial trace of d minus beta rho. Okay, any questions?
Where did the integral over alpha go?
Is 1.
But how can you take that integral to be 1 when there's alphas outside of it? When there's like other alphas there that are involved?
Right. Right. Okay, keep it outside. Thank you. Keep it outside. Thank you. Yes, that's something that it's a step that I'm missing here. Yeah, you're totally right. Let's do that. I will erase this. I will do 1 divided by pi squared, integral of d2 beta alpha, and I have alpha alpha. Good. Are you happy? I think that's something that I missed in the calculation. It should not be absolutely. It's not a big deal. So it is 1 divided by pi square or pi integral of d2 alpha. 1 divided by pi. I missed a step in my notebook. So I get summation of m and n alpha star beta power of m minus alpha beta star power of n divided by n factorial m factorial, the trace of d minus beta rho. Okay, and then parenthesis closed, then I have alpha alpha. All right, I think you're happy with this. The summation is over m and n, and this is the summation that we do have. What is this term? The first one is summation over m of alpha star beta power of m divided by m factorial times summation over n minus alpha beta star power of n divided by n factorial. What are those?
Exponentials.
Exactly. This is exponential of alpha star beta, and this is exponential of minus alpha beta star. True? Good. So then we do get 1 divided by pi integral of d2 alpha, 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 then 1 divided by pi integral of d2 beta, exponential of alpha star beta minus alpha beta star, trace of d minus beta rho. Good. Sorry guys, I'm getting tired sometimes. It's 3 hours on row. And he's not writing on the boards that I can see from big far away and then analyzing it. Good. Look at that. I want to do a little bit of changes. Let's change any beta with minus beta. Okay, because I don't like to carry minus beta here. I want to simplify that. Any beta to minus beta, then this integral will be inverted. Then we will get a minus sign, then which goes back again. So we will get 1 divided by pi integral of d to beta exponential of alpha beta star. That will be swapped. Okay, remember that exponential term will be swapped minus alpha star beta trace of the minus. I'm doing this calculation just to take away the minus sign of rho. Good. Fantastic. Remember that we do the integration on beta, so it doesn't matter really if you do the change of variables. Yes. 5 minutes. Merci. Okay, so we do have this expression. I call 1 divided by pi integral of d to alpha, alpha, alpha. This function that I have it here, it's a function of alpha. I will call it, let's look at the notation if we want to have pi. Yes, we do have pi, yes, okay. Yeah, that's fine, that's fine. I call it W of alpha. I was just worried about the normalization factor, which is fine. If we don't have it, then we will add a pi in the calculation. What is W of alpha? Remember, we define it as 1 divided by pi integral of d to beta e power of alpha beta star minus alpha star beta trace of d beta of rho. Good. Okay. I will write it as a trace of rho operator times a t operator of alpha with this t operator and times, of course, we need another factor of pi, which is fine. Yeah, let's call it 1 divided by pi, which is this t operator of alpha, which we'll talk about that next time, which is look like the characteristic function is integral of e power of minus alpha beta, alpha beta star minus alpha star beta, and then we have a d operator of beta. Yeah. Okay. And we know that d operator is exponential of beta star A minus beta, beta A dagger, beta star A. And then this integral is given by d to beta, e power of beta A dagger minus alpha star plus or minus, I think it should be plus. let's check it, beta star, and beta, then a dagger, a minus alpha. Yeah, this is what we will get. You have to cast them together. You have these exponential term, you have the other exponential term here. And remember that this one is just a parameter that you can insert it inside of exponential. You can join them together and you can cast them together in a proper way. And what you will get this expression. Okay. If this is done in the normal order or anti-normal order, then that will be the orthogonality function, and it will give you the delta function, delta of a dagger minus alpha star, and delta of a minus alpha, which in this case it is the sigma order. Okay, I think I will stop here because it's almost 7 minutes past. I just want to reach to this point. Please redo the mathematics at home. There might be some minus sign that I missed, and my apologies for the part that in my note I had a jump, so I didn't have it properly. But anyway, this is the basis that you need to get the probability distribution. And the T operator is something like a Fourier transform of displacement operator. So if you look at that, it seems that you do the two-dimensional Fourier transform of the displacement operator, and you will get a new operator, which we call it the T operator. Next lecture, we drive the Wigner-Hosimi and Wigner function, Wigner distribution, Hosimi function, and Glauber representation, also for specific cases. Is there any question?
I had one last question about the exam, one of the exam questions.
Okay, let me stop this. Sorry.